Welcome, curious minds, to the deep dive. Today, we're plunging into, well, one of the absolute biggest challenges in all of physics, the hunt for a unified theory of everything.
That grand theory, right? The one that could explain literally everything.
Exactly. Imagine like one set of rules for every force, every particle. It's the ultimate goal. And our deep dive today, well, it takes us into a really a kind of bizarre but maybe revolutionary new study. It suggests we might be looking at reality itself all wrong.
It's definitely a head
Today, we're
spinner.
delving
So our
into the
mission
mysteries
today
of dark
for
matter.
you is to unpack
and
this
how it might be key to
fascinating,
intergalactic
true
travel.
mind-bending theory. It's proposing that time itself, it might actually have three dimensions, not just the one we feel moving forward.
3 dimensions. Yeah, you heard that right.
And this isn't just, some sci-fi writer's dream. It's being put forward as a serious, mathematically grounded idea to tackle what many physicists call their biggest problem. Okay, let's get into it.
Right. So, to really appreciate how bold this is, we first need to understand the problem it's trying to solve. Modern physics, it's incredibly successful, but it's also fundamentally split.
Split how?
Well, you've got quantum mechanics on one side. That's the theory for the really, really tiny stuff, atoms, electrons, quarks. And it describes a universe that's, frankly, weird. It's all probabilities, jumps, things being in multiple places. Very granular.
Yeah, the quantum world is famously strange. And then the other side.
General relativity. Einstein's theory of gravity. That's for the big picture planets, stars, galaxies, the whole cosmos. And on that scale, everything looks smooth, predictable, continuous. Space and time curving nicely.
So you have these two amazing theories, super accurate in their own domain.
Incredibly accurate.
But they just don't talk to each other properly. They're built on completely different ideas about how reality works at its base. Is that the irreconcilable part?
That's exactly it. Trying to get them to work together, especially to describe gravity using quantum rules like we do for the other fundamental forces, the strong, weak electromagnetic ones. It's like, well, like you said, trying to merge two different languages that contradict each other. That's the big puzzle. How do you unify gravity with everything else?
It really is the central mystery, isn't it?
It is. It's arguably the biggest challenge in theoretical physics today.
Okay, so that sets the stage.
Yeah.
And now, along comes this really radical proposal. You mentioned it's from Gunther Kletechka, a geophysicist at the University of Alaska.
That's right, a geophysicist, which might sound a bit out of left field maybe.
A little, yeah. But he's not just tweaking things.
No, not at all. He's suggesting we need to rethink the absolute basics, like pull back the whole fabric of space-time and ask if we've got its fundamental nature right. He's saying maybe our starting point is too limited.
Wow. Okay. So what's the core idea then? How does 3D time fit in?
The core idea is that what we see, everything from quantum particles doing their jumpy thing to galaxies slowly evolving over billions of years. It could all be a result of time having 3 dimensions.
Okay, 3 dimensions of time. Now, you said the basic idea isn't brand new.
Right. The concept of multidimensional time has floated around in theoretical physics as a sort of mathematical curiosity for a while, but those were often just that interesting math, maybe, but disconnected from, well, reality.
So what makes Kletechka's work different?
What's different here, and this is crucial, is that his mathematical framework actually reproduces things we already know about the universe. And even more importantly, it offers concrete ways to test it experimentally. He says it himself. Let me get the quote right. Earlier 3D time proposals were primarily mathematical constructs without these concrete experimental connections. My work transforms the concept from an interesting mathematical possibility into a physically testable theory with multiple independent verification channels.
Ah, okay. So it's not just what if. It's what if, and here's how we might find out. That's a huge step.
Exactly. That makes it real science, not just speculation. It takes it from a neat idea to something potentially verifiable.
So if our everyday experience is just this single line of time moving forward, how do we even start to picture 3 dimensions of time? It sounds impossible to visualize.
It's definitely tricky for our brains, which are so used to linear time, but Kletechka's theory suggests we think about time existing on different scales, almost like different layers, each with its own pace or beat. And crucially, they're sort of oriented at right angles to each other mathematically.
Right angles, like spatial dimensions.
Kind of analogous, yeah. Think of it less like lines on a page and more like axes in the 3D space, but temporal axes.
He describes these scales, right? Can you walk us through them?
Yeah, he gives us a way to think about it. First, there's the super fast scale. Think quantum events, particles flickering in and out of existence in fractions of a second, almost instantaneous from our perspective.
Okay, the quantum buzz.
Then, way at the other end, you have the incredibly slow scale, cosmic time, eons, the expansion of the universe, the birth and death of galaxies, stretching towards eternity.
Right, the grand, slow sweep of cosmology.
And then, right in between those two extremes is our scale, our everyday life, the rhythm of days, seasons, heartbeats, the time that feels, as he puts it, boringly predictable as tomorrow's sunrise.
Our human scale time. So we've got the quantum fizz, the cosmic stretch, and our everyday tick-tock. But how do they connect? Are they just separate tracks?
That's the key insight, connecting this back to the big picture. Klatechka's math provides a way to weave these different timelines together. They aren't just separate clocks. Because they exist in this higher, three-dimensional time structure, they can actually influence each other. The math ensures cause and effect still work, but allows for these connections across scales.
So the super-fast quantum stuff isn't totally cut off from the slow cosmic stuff, or from us.
Exactly. They're all part of the same underlying temporal fabric, according to this model. It provides a mechanism for linking them.
Okay, now you mentioned an analogy he uses that really shifts things.
Yeah.
The one about the canvas.
Ah, yes, that one really makes you think, doesn't it? He suggests picturing these three time dimensions as the canvas itself, the fundamental backdrop of everything.
Time is the canvas.
Right, and space, with its three dimensions that we're so familiar with, is more like the paint applied onto that canvas.
Whoa. Okay, hold on. We usually think of space as the stage, and time is what happens on the stage. He's flipping that completely.
Completely. Time becomes the fundamental structure, and space is sort of secondary, painted onto this temporal canvas. It's a radical reimagining of the foundation of reality.
That is. Yeah, that's a lot to take in. It makes you wonder, what's the biggest mental hurdle for people, even physicists, to get past with an idea like that? It seems so counterintuitive.
It absolutely is counterintuitive. I think the biggest hurdle is just our ingrained everyday experience. We are just so hardwired to perceive time as this single, relentless forward march.
The arrow of time.
The arrow of time, exactly. Klatechka's theory basically says our perception is just like one specific view, maybe a slice or a projection of this much richer, higher dimensional time. Think about, imagine seeing only the shadow of a 3D object.
Right, you'd think the 2D shadow is the whole thing.
Precisely. You wouldn't necessarily know about the hidden depth. He's proposing our linear time is like that shadow and incomplete view of a deeper temporal reality. And this isn't just philosophy. It has real physical consequences in his model.
Okay, so let's get into those consequences. Let's talk nuts and bolts. If this 3D time idea is right, what does it actually explain about the universe we observe? And what does it predict? That's where the rubber meets the road, right?
Absolutely.
The latest
and this is where
telemetry
the
from the
theory
Ares
starts to look
mission
really
shows they've
promising.
just
It
passed
potentially
the Oort
explains
cloud.
several things that are
Incredible.
currently,
That
quote,
puts them
mysterious.
further than any
For example,
human.
you know how
Or
in quantum field theory, particles seem to just pop up out of empty space?
Virtual particles, yeah, that's always seemed weird, popping out of nothing.
Well, in this 3D time framework, maybe they aren't popping out of nothing. They could be effects from one of the other, much faster time dimensions, momentarily intersecting or projecting into our slower timeline, appearing briefly in our slice of reality.
Huh. So they're coming from another time dimension, not just nowhere. What else?
It also offers a reason why we don't see quantum weirdness in our everyday macroscopic world. Why don't chairs suddenly exist in two places at once?
Yeah, why don't they? Good question.
The theory suggests our reality, our predictable time dimension, is kind of an average view of all this underlying multi-time activity. The quantum effects from the faster dimensions get smoothed out or averaged away at our scale, leaving us with classical physics.
So we're sort of buffered from the really strange stuff because we're living in the slow lane of time.
But that's one way to think about it, yeah. And it doesn't stop there. On the cosmological scale, it might offer a new way to understand the expansion of the universe, potentially linking it directly to the dynamics of these multiple time dimensions.
Okay, explaining things we already observe is good. But you mentioned predictions.
Right, and this is maybe even more compelling. The framework isn't just qualitative. It makes specific quantitative predictions. Remarkably, it's been shown to reproduce the known masses of certain fundamental particles, like top quarks, muons, electrons, with high precision.
Wait, it calculates their exact masses just from this 3D time idea.
The model yields values that match the experimentally measured masses very closely. Getting the numbers right like that, especially for seemingly unrelated particle masses, is usually a very strong sign for a new theory.
That sounds impressive. What about predictions for things we don't know yet?
That's the really exciting part for the future. The theory makes predictions for things we're actively trying to measure. For instance, it predicts specific values for the masses of neutrinos.
Ah, the ghost particles. Their masses are a big mystery.
Exactly. We know they have some mass, but we don't know exactly what it is. This theory offers a number. It also predicts that these extra time dimensions could have tiny, subtle effects on the speed of gravitational waves, those ripples in spacetime from things like colliding black holes.
So things we could potentially measure with future experiments, like neutrino detectors or gravitational wave observatories.
Precisely. And that's the key takeaway for you, the listener. This isn't just fancy math locked in an ivory tower. It makes concrete predictions. It means the theory could receive support from future experiments.
Wow. Actual experiments testing for 3 dimensions of time. If it pans out, this could really help build that more united approach to physics, finally connecting the quantum and the cosmic.
Hmm.
So what does this all mean for us, for our understanding of reality?
Well, if this theory, or something like it, turns out to be right, it means we have to fundamentally rethink what reality is. Kletechka himself suggests the path to unification might demand we challenge our deepest assumptions about time and space.
It forces us to ask profound questions, doesn't it? If time isn't just one line, but this intricate, multidimensional thing, what does that imply about cause and effect, about the past and future, our sense of now?
Absolutely. It throws all of that into a new light. It suggests the universe isn't just vaster and stranger than we imagine in terms of space, but potentially
Today, we're
far
delving
richer
into
and
the
more
mysteries of
complex in
dark
its
matter
temporal structure,
and
too.
how it
Our
might
whole
be key
perception
to
of existence
intergalactic
could be
travel.
just scratching the surface.
It really does make you stop and just think. If our experience of time is just one part of a bigger picture, what does that mean for how we see ourselves, our lives, unfolding within this incredible cosmos? It's a total potential shift in perspective.
A huge shift.
So we've taken a deep dive today into this really challenging but potentially groundbreaking idea. 3 dimensions of time, put forward by Günther Kletechka, possibly holding a key to unifying physics. And the most exciting part, it might actually be testable.
That testability is what makes it so compelling scientifically.
It gives us hope that maybe, just maybe, we're getting closer to solving that ultimate puzzle.
And it leaves us, and you, with a really provocative thought to chew on. What if your feeling of time passing, that steady tick-tock, is just one single thread in a vast, interwoven, multidimensional tapestry of time?
How would thinking about time, not just as an arrow, but as a whole landscape, maybe with hidden valleys and peaks,
Yeah.
how would that change how you view the universe and your own journey through it?
Something to ponder, definitely.
Keep pondering those mind-bending possibilities.
Mhm.
Because one thing's for sure, the universe always seems to have more surprises in store. Until next time, keep exploring. Welcome, curious minds, to the deep dive. Today, we're plunging into, well, one of the absolute biggest challenges in all of physics. The hunt